patience, and thanks also to Boris for all his hard work in setting up the hybrid setup. So today we have Dr. Jana de Wiljes from the University of Potsdam. She's our first in-person speaker, which is very exciting. She's also a principal investigator on several projects in a collaborative research center on data assimilation, mainly based in the Berlin area in Germany. Her research spans sequential Bayesian inference and reinforcement learning with applications in weather and climate and pharmacology. And today she'll talk about a variety of challenges in high-dimensional nonlinear filtering. Jana, the floor is yours.
Thank you, Sahani, and thank you so much for making all of this happen despite you being in Europe. Yeah, I don't even know what the time right now is at your end. So thank you for setting everything up and having me. As you said, I will be talking about challenges in high-dimensional filtering. I'm assuming not everybody is familiar with data assimilation, so let me jump into explaining what the concept is. Sorry, I have to adjust the size here. Is that better?
Yeah, okay. That's good.
So first of all, what is data assimilation all about? So it's really when you kind of have a model and some data, and you're trying to join these two informational sources to reduce the uncertainty when it comes to predictions. And the go-to example where data assimilation became was developed mainly is actually American weather prediction. And it's still the go-to example because it combines all of the main challenges that we still face in data assimilation. So the model are typically evolution equations, ODU, PDs, and the data nowadays, so back in the day, it was actually not that much data, but nowadays we're entering the realm of amounts of data where people are thinking about actually doing purely data-based methods. And of course, this whole setting where you have some kind of model that is describing a system of interest and you have some data, you of course have in many application areas. And just to start off with, I'm going to give you one more concrete example, that is space weather. So we do actually have a project on this. So for those of you who have not heard about the term, so the term space weather is actually a little bit misleading because it has nothing really to do with what we consider to be weather, but it's actually about solar storms, so electric particle in the near Earth area. And there are different belts that people are kind of considering looking at. So you can kind of look at the area that is closest to Earth, which is ionosphere. And then there are different belts, radiation belts and ring currents that you could also consider. And essentially the sun is charging particles, which is leading to what we call solar storms. And they can affect anything in space, so satellites or also with astronauts, and but also can actually affect electronics on Earth. So there have been events where this has happened. And regarding the satellites, I think in February of this year, Elon Musk lost 40 satellites he just launched, and there's billions of dollars that were immediately gone due to one of those solar storms. And since nowadays we're I don't know about you, but I cannot find my way anywhere anymore without my phone. And as soon as the satellites are down, we have big issues, and that's why people care. And it is actually also affecting weather on Earth. And for example, one effect everybody knows is polar lights. But the other thing is, as soon as we don't have satellites, an American weather prediction on Earth also becomes hampered a lot because you need the data coming from the satellites. And for example, planes don't start if the weather system in Germany is down. Planes don't start anymore. So just to finish this whole motivation about this application area off, we have a real-time prediction of this is actually the radiation belts, one of the belts happening in Potsdam at the GFZ, and they're using data assimilation to update, I think think every hour they update with the new incoming data and predict what the phase-wise density of those particles are. So let's get down to the mass. So we, as I said, we have a model and some observations. And what we typically, so I'm going to try to use a system. I'm a little bit afraid to break everything. I hope you can see it. So we have this model and we have the observation. And the model here, I'm assuming, is going to be an ST, and so are the observations. Of course, in practice, we will have discretized versions of these. And often people consider, for example, in numerical weather prediction, discretized PDEs for the model, at least in numerical weather prediction. I'm going to start off in this continuous setting because I'm actually going to prove certain things when it comes to accuracy and stability of the methods that we're going to consider. And in this setting, it's not tied to any discretization, so it's much nicer to consider it in a continuous setting. So what is the quantity or that we actually want to consider? That's the so-called filtering distribution, which is just the distribution of the signal of interest, which is here given by our model, and condition on all the data up to a certain time point. And typically, we do actually know how this distribution evolves. It evolves according to the Kushner-Stratonowicz equation. But typically, for any larger dimensional problem, we know there's no analytic solution for the Kushner-Stratonowicz equation. Nevertheless, we will make use of this fact later on. At least interrupt me at any time if you have a question. I'm trying to look at the chat as well. So in the linear setting, when our evolution equation, so our drift is essentially linear, and so is our observation operator, which was the H on the previous page. Then everything, we do actually know what the filtering distribution looks like, because it's just a Gaussian. And then we just need to know how the first two moments evolve. And these equations have been known for I don't know, 60 years now. They're called the kamagusi filter. And what you can see here, the first equation is just the evolution of the mean. And there's a similar equation just for the second moment. And the problem really arises when the model is nonlinear. And in that setting, we have no idea what the analytic structure of the filtering distribution is. And one way to kind of circumvent this problem is, of course, to say, okay, let's just consider it empirically, which in theory is a good idea. So we just want to have samples of this filtering distribution. But of course, we need a lot of samples. And one thing that is typically being done is because we have the model, which we can generate samples with. And all of those samples we can actually then, for example, we use impedance weights through the we use the likelihood that is considering the data. And these importance weights are given here, for example. And this answer is called sequential Monte Carlo, or importance sampling, or in the community also particle filter. But the issue is, of course, we need to generate a lot of samples with the model. And typically those models are so high dimensional that you cannot, even with a supercomputer, generate more than 200. And for example, in the numerical weather prediction setting, your state space is 10 to the power of 8. And 200 is obviously nothing in this type of setting. So those particle filters, sequential Monte Carlo, as all Monte Carlo methods obviously suffer from the curse of dimensionality. And somehow people had to make it work, or they were faced with the issue that they have only 200 samples. And they somehow have to find a method that will still, giving us good predictions with such few samples. And one thing people do is, despite being in a nonlinear setting where you know that the posterior is actually not a Gaussian, you would like to have similar evolution equations, like in the linear case, where you just know how the first moments evolved. It would be nice to have evolution equations just for the samples in time, and then you could generate samples of the posterior distribution. And with this idea in mind, because this would solve, the nice thing about the linear filters is that they actually move the particles around despite just weighting them. Because if you don't start off with a nice set of samples that is covering the ground of your state space well, then your importance weights will become zero very fast, and then you don't have anything anymore. So the idea of this moving them towards the observations is then supposed to help circumvent this whole problem of the high dimensions. So what you want to have is something similar to what we had before. So you want to basically add, you want to modify the evolution equation with such a control term where the data is coming in. And since we know, so what you can do then is look at the Fokker-Planck equation of this, which gives you the associate density, or the evolution of the associate density. And since we do know how that the posterior density or the filtering density is actually evolving according to the Kushner-Slatonovich equation, we can now compare this Fokker-Planck equation of the modified evolution equation with the one with the Kushner-Slatonovich, and then try to see how do we have to design this additional factor here so they're actually equal, and I'm actually producing samples of the true posterior. And with this idea in mind, Pasha Neta and Sean Main and collaborators came up with the so-called feedback particle filter, and they did exactly what I just described. They wanted to basically make the Fokker-Planck equation of the modified evolution equation equal to the Kushner-Slatonovich equation, and they used the Kullback-Leibler divergent to compare the two vectors or densities here. And what they came up with was actually that if you choose this control, this unknown factor here in the modified evolution equation, if you choose it to be the solution of this weighted Poisson equation here, then the two will become equal. And this is of course very neat, and you exactly have what you want. The bad thing at this point is that solving a weighted Poisson equation that depends on the unknown density, which is in here, is still a very hard problem. But from a theoretical perspective, this is a very neat thing to have, that you now have actually a modified evolution equation, even in the nonlinear case, that tells you how to generate samples from this, from this density. And at this point, at least, you can then again come up with new ideas to how to maybe approximate the solution with something lower dimensional, and then design filters on the basis of this. And actually, Sahani has some really interesting work out on this, because this is not the only way how you can get to such a modified evolution equation, and there's different variants of these weighted Poisson equations that lead also to different types of filters. And yeah, it's definitely worthwhile checking out her work. It's really interesting to see how she brings together all of these different filters. So right now we're at a point where we need to make some kind of approximation, and the strongest approximation would be to just say, okay, we choose our gain to be somehow constant. And this leads to a filter that is called the ensemble kamagusi filter, which then, which is actually just it's very related to the kamagusi filter, hence the name. So essentially, it's just that despite being in a nonlinear setting where your evolution equation is actually the drift is nonlinear, you pretend that the posterior is a Gaussian, and then do a Monte Carlo approximation of it. And then the evolution of the individual ensemble members, so the individual particles, will be according to this evolution equation up here. And just in terms of this, seems to be maybe very abstract and not very practical, but in fact, the discretized version of this is being used in several centers. For example, the German Met office uses in the discrete, like the discretized version of this, which is called the ensemble Kalman square filter, or for people who know the family of filters, LNTTFs are being used here. And this is a very stable method. And despite the very strong assumption that you're pretending everything is Gaussian, despite it being far from Gaussian, it works very well in practice. And the predictions are quite accurate. And this has been used for many years in practice, but from a mathematical point of view, it has actually not been very well understood, like what the properties of these filters are, and if we can show some kind of level of accuracy. And yeah, in the last, let's say, 8 years, people have started to look at this. But since it is actually not reproducing the true filtering distribution, it's hard to kind of say, okay, what do we actually want? And one thing people want in practice is that the tracking error is small, because you kind of want that it doesn't deviate too much from the truth, essentially. And that's why my collaborators and I started to look at this for this particular filter. And there's also some work out there, because we still will be staying in the continuous setting and considering this filter you see up here. Or actually a modified version, but I will get to that in a second. And a lot of discrete filters, if you look at the time limit, actually converge to this. So as soon as you show something for this continuous version, you're covering a lot of ground on the level of the discrete filters. So there are a lot of details I'm going to jump over today, but if you're interested in what the exact things were, please don't hesitate to contact me. So one thing will be that we actually also modify the noise here, and we also like replace it by an interconnecting particle representation that here depends on the spread of the ensemble, essentially. And we do that to actually more easily grasp the bounds of this filter. Another thing we do, and this is also something that is done heavily in practice. So to make these filters work, so if you think about it, even if you have this Gaussian approximation, of course, if you have 200 samples and your state space is 10 to the power of 8, 200 samples are not going to cut it. Especially this covariance matrix, which is just an imperial covariance matrix, is going to be highly, like not invertible at all, but it's not very stable either. There could, for example, be spurious correlations that don't actually exist. And due to the fact that in numerical weather prediction, it's well understood that there shouldn't be a correlation, for example, between the weather in Berlin and the weather on Hawaii. So since we know that, we can just set those correlations to 0 and just say, okay, we know that there's a correlation span, like the Berlin weather is still affecting kind of the, up to a certain radius around Berlin, but other than that, it doesn't. Of course, this always depends on the different physical information you're looking at, But this is kind of a reasonable assumption, and setting stuff to 0 in the covariance matrix is called localization in the community. And we also do just that in our filter. It is actually also necessary to actually derive these bounds, just for the simple reason, as I already said, that the covariance matrix otherwise has really bad real post. But it's also not a completely unreasonable thing, because that's, as I said, is exactly what you do. So what is changed up is the covariance in here and also in here. Here it's actually changed a little bit more strongly, because there we essentially only take the values on the diagonal and work them. And now let's get down to what we actually showed. So just again, a few assumptions. I'm going to focus on what is up here. Another thing is, again, this is like when I talk about 10 to the power of 8, the reason it's so large is not because we're going down to such a fine grid. You could do that, obviously look at just a very small space, and then you go really, really fine in the grid. But that's not what we do. The grid is still several kilometers maybe, but it's just that the space you're looking at is very large. So what you do have is short range interactions. That's an assumption that we needed to make, but it essentially just means that one grid cell is not affecting grid cells that are super far away. It goes in the same direction of the localization, but this is now in terms of the model. So yeah. It has to do with how much we think that something. Okay. So that's the key assumption we have. And just to give you an idea of what else we need to assume, those things are really bad if we don't. So this is the Lorentz system, which is the go-to toy example when you do look into anything that is weather related, because although it's just three-dimensional, it already has all the properties that, again, are super challenging in the data estimation setting. So on the left-hand side, you see, so the blue one is the reference, which is just the attractor of the Lorentz system. And since, then the purple, the pink lines, is the prediction that is using data estimation techniques to kind of approximate the reference solution. The pink one is observing, I think, the first component. So the Lorentz system has 3 components. And on the right panel, you see what happens if you observe the third component. So this is well known that if you just observe the third component, you don't have enough information to actually fully recover the reference solution anymore. And due to this fact that you have to basically ensure that you're observing the right things, we, as a first step, said, okay, we assume that we observe everything. If you know your system well and you know what to observe, you don't need to assume that. We're actually currently working on doing just that. But essentially, you cannot just use the general drift function. You need to say, okay, I know this function well now, I know the system, and I know what to observe. And in the community, of course, for like many systems, we have been looking at this for years and know what to observe and what not. But since we wanted to stay a little bit more general, didn't want to focus on just one model, we just said, okay, let's observe everything. And the first thing you need to do if you kind of want to look at tracking ability is that you need to ensure that it doesn't, the filter doesn't blow up. What does that mean? It means exactly what you see here on the right. This is when the filter blows up and covariance becomes huge, essentially. And the other problem would be if it collapses and basically falls onto just one particle and doesn't cover enough of the ground anymore to truly reflect what is happening in the signal. And so the first step is essentially showing that this is not happening. And to show this, you show that there's a bound on the covariance matrix. We did derive bounds for the covariance matrix that of order epsilon squared, and epsilon is the order of the observation error. And having this, one can then move on to actually look at the signal tracking error. For that, we're also able to derive bounds. So again, you cannot really expect more due to the fact that you know that it's not doing anything right when it comes to the actual distribution. But having this is already enough, because if you're predicting, you just don't want to be far away from the true signal, and then you're doing okay. So for a single time step, so the ET here is just the difference from the reference solution. Again, we're able to derive a bound of order of epsilon squared. The biggest issue to basically be full disclosure here, the bound obviously also depends on the dimension of the state space, which at this point feels a little bit of a letdown, because this can be huge. But it's what is to be expected, because even if you do a very, very small error in each of the components, this will obviously add up to something larger if you look at huge states. And it's at this point not even clear if it's just in one component, but that's something we look at after this, to at least ensure that in each individual component, it actually doesn't depend on this on the dimension of the state space. So you can be sure that in each individual component, you're actually only making a very small error. And then you can actually also look at a uniform bound for a fixed time interval. And again, we were able to derive a bound. As you can see, here the order epsilon squared comes in again. And you of course have now dependencies also on the t, but it's all since the t is just coming here in this log, it's not too bad. So up here you can see, so we derived this bound theoretically, obviously, but then we also wanted to look at if numerically we're also kind of getting the same results in terms of the bound. And what you're seeing up there is we're also able to numerically verify our theoretical results. Now, as I already kind of hinted at, since the error for the fixed or also the uniform error do unfortunately depend on the dimension of the state space, we wanted to look at the individual component and at least ensure that we can show there that the bound doesn't depend at all anymore on the dimension of the state space, and we're able to show exactly that. So you then get a bound that is just of order epsilon squared, which is really neat because that's very small, and you can actually ensure that you're only making very small errors in each individual component. And again, you can do the same thing also for the uniform error, and the same is true here as well. So in terms of these bounds, for these particular type of filters, these were actually the first kind of bounds of this kind to be shown at all for these filters. And these filters had been used for years in those big centers. So, I mean, at the centers, we're kind of happy already that everything was working fine. But of course, it's nice from a mathematical standpoint that we can also verify that it works. But the work is far from done here, because we did actually use a fairly idealized setting here. I already told you we observed everything. And that's the first thing kind of to tackle, because that's very unrealistic. There's a bunch of data out there nowadays. But the next big thing would be to say, okay, we need to assume that we don't observe it. And the one thing would be to say, okay, I'm looking at a certain ODE and PDE. I understand this ODE and PDE very well. I know what components to observe, and then I can at least work with that assumption. Then I'm assuming that I'm actually observing at least the relevant components. In practice, of course, you can not always be super picky of what you can observe. So there's still a stretch to go to the real application, but we're slowly but steady getting there to make it very realistic when it comes to the true applications. Another thing is, if you say, okay, I actually want to look at it a little bit more general, and don't want to look at the specific equation, one question would be, if you just don't observe everything, but switch between the components of the state space you do observe, a little bit in the fashion that is being done, for example, with stochastic gradient descent, where you only like choose some parts of the sample and don't work with the whole batch. From the application point of view, this is becoming more and more relevant because stochastic gradient descent was kind of developed out of the necessity that it was too much data and you just couldn't use all of it. And this is starting to happen actually as well in this kind of community. It didn't used to be a problem at all, but at this point we do have large amounts of data and they're already kind of not using everything they have. Even for the reasons that they don't want the data to be correlated and stuff like this. So it is becoming a more and more realistic kind of thing also in application. And then the question is it sufficient if it just switch between things that I observe, between time steps, that if I just observe every component with a certain frequency, that I still get the same kinds of bounds? That's something currently looking. Let me see. Should maybe hurry up a little bit. Now, this was all for this kind of assumption that the gain was a constant gain, which gets you into this approximate Gaussian setting. But of course, people in the community want to do more nowadays, because this Gaussian approximation has been around for many, many years. And despite it working very well, the idea is to somehow at least capture the nonlinearities a little bit better. And the idea is to say, okay, how can we do that? Maybe we can find some higher order approximation of this gain, and then develop a filter that is going beyond this Gaussian assumption. It probably will still not do the consistent thing, because you do have to do some kind of approximation. And there's many things that are out there. Actually, Sahani has looked into a diffusion map approximation for the feedback particle filter, and has also derived some really interesting things there. So you should definitely check it out. And one thing would be, if you have some kind of different gain here, what you could maybe do is mix the Gaussian approximation with this more elaborate gain to then get a higher level of accuracy, but at the same time still have some level of robustness. Because one thing that people are struggling with right now is every time they leave the realm of the Gaussian approximation, everything becomes super unstable, and it's super hard to use the Gaussian setting just because it's so robust. But these kind of hybrid filters that are out there, and we've been looking at these type of filters, at least in the discrete setting a lot, seem to be kind of beating the individual filters that are either Gaussian approximation or some kind of approximation of the more consistent filters. So it's a very interesting field and definitely something worthwhile checking out. And now, I know we started a little bit later, but I will hurry up now to finish on time. I know you have an important meeting at 4. Just to finish up, I wanted to show you another really interesting application that we're currently working at. It's what you see right now here is a graph about model-informed precision dosing, and it shows you the state-of-the-art methods that are out there. And I don't really have time to go in a lot of detail into it, but what you have to imagine right now, a physician that is dosing you for any kind of disease and giving you some kind of drugs, would just be looking at some kind of table and say, okay, you're maybe male, you weigh a certain amount, you're a certain age, so you would be getting a certain amount of this specific drug. And the physician, in best case scenario, would look at a table to kind of figure this out. In most cases, they would just give you the same amount, no matter what age, gender, height, or whatever you are, because that's the FDA approval and that's it. But of course, it's well known that people react very differently to the amounts of drugs. And this is very important. So people have decided to look at methods that go beyond this and consider more of the covariates and collect data along the way. And one thing you can do then is you can say, okay, I have some kind of model that is describing how a patient should react to the drug. Of course, these models are not perfect, and human is very complex. But then is every time the patient comes into the doctors, the doctor collects some kind of data. It could be, for example, blood concentrations. The problem or the medical application we're actually looking at is chemotherapy. So there, what you see the curves down here is the neutrophil counts of a patient on like the average neutrophil count of patients that are receiving chemotherapy. And the black points are the data points, and then essentially you update the model parameters to the patient, so it becomes personalized every time, because unfortunately the patients come in all the time. And what you can do then, after you collect this data and essentially perform data selection, you can do reinforcement learning to actually find the optimal dosing for that specific patient. And that is something we have been doing for some time now. And it's a very interesting setting where, yeah, machine learning is, I mean, there's many areas where machine learning is coming together with more classical inference. And one really nice way how you can describe it is so-called sequential Monte Carlo research. So I don't know how familiar you are with reinforcement learning, but Monte Carlo research is a method that has been used, for example, for AlphaGo, AlphaZero. Actually, I haven't checked out AlphaStar yet, but so all of those things developed by DeepMind that have been beating the best Go players and chess players and so on. And essentially what you have is you're trying to approximate this expected value here. That's the goal in the reinforcement learning problem. And this is done again in Monte Carlo fashion. So you essentially just generate samples, what I call psi here, which are combinations of states and actions. And if you can generate a lot of them, you can of course approximate this Q up here very well. And the problem sometimes is you cannot actually generate samples of the actual setting mode, but you might have a model. And then you also might have data. And then what you're in is kind of a sequential Monte Carlo research setting where you can generate the samples for the model, but then you need to update them frequently with the data coming in to actually get a sample of the true system that you're trying to consider. And at the same time, you have this control parameter coming in, which is here the A, is known as action. And in the dosing setting where we're kind of treating patients is of course the amount of dose we're administering for a patient. And yeah, this is just only hinting at what we've been up to in that setting. But again, this is where data assimilation is crucial. And combining it here with the ideas of reinforcement learning is really very neat. And this kind of decision making under uncertainty is of course not only relevant for the medical realm, it's of course relevant in many application areas. I'm currently looking deeper into it, and not only like developing algorithms, but also looking into uncertainty quantification, because of course it's very relevant, especially in the medical setting, to also understand what kind of errors are you looking at if you do all of those approximations, because you don't want to just dose a patient based on something the algorithm spits out and not be sure what you're going to do to the patient. And I think I am out of time. Yeah, thank you so much for having me. And if you're interested in any of this, yeah, please contact me. I'm happy to tell you more.
Sorry, do you want me to take the questions?
Yeah, that'd be great.
So let's see if there is any question from the audience. No. Anyone here has a question?
Yes. So Boris, can I ask a question?
Yeah, go for it, Robert.
Okay, thanks very much for a great talk, actually. I have first question is, what do you do about parameter estimation?
In a specific application or in general?
Let's try, well, in the models that you looked at, they have a lot of parameters as well.
Yeah. So one thing you can do is you can, if you look at state and parameter estimation, what you would do is you just augment the state space with the parameters and try to estimate them simultaneously. And obviously this is a super hard problem because if if you change the parameters slightly and this is heavily affecting your system, you will be in a lot of trouble, and often you don't really know how so you're basically coming up with a model how the parameters evolve in time, which is often just chosen to be a random walk, for example. And sometimes it's very hard to then, if you're super far away with your initial assumption where like the parameters should be, it's really hard to maybe then end up with the true setting of the parameters. Nevertheless, when people do this, and if you're not too far away, you might get away with this, but it is still a very challenging problem. And of course, you can also use it, these methods, you can actually also use in the more classical inverse problem setting, where you don't have a time, like you don't have a state, but you have the classical parameters. And what is often done then is you assume that like a synthetic time and just slowly try to absorb the information from coming in from the data. And these techniques, so it's kind of like a tempering attempt to just using Bayesian methods for inverse problems. And those seem to be working much better than just going using the typical Bayesian ansatz where you just have a prior and then use the whole data as a batch. So you can still use those methods. But yeah, I hope I answered the question in a direction you kind of were looking for. I don't know. If not, please let me know.
Okay, Boris, can I ask a second question or not?
Yeah, go for it.
Okay, thanks. So these are interesting methods. Now, we've got, well, people have much smaller dimensional problems, but particle MCMC is still very expensive. So I wonder if you've tried these methods on 20-dimensional problems, 30-dimensional where the state is high dimensional, and to see if these methods are as good as or nearly as good as, say, particle Gibbs or the particle Metropolis Hastings and things like that, which actually don't work that well. Well, the PMH doesn't work that well in high dimensional state space models.
Mm-hmm. So definitely, so you essentially the biggest question, so in for lower dimensional state spaces, when you can generate a lot of samples, something like important sampling or sequential Monte Carlo would be preferable over the Gaussian approximations. But as soon as you kind of in this area where you have samples, maybe also not like a few, but more, but you're still not like covering the state space well enough, because this could already happen in 20 dimensions. So like the Lawrence 96 model, for example, smallest version will be, for example, 40 dimensions. Sequential Monte Carlo or particle filters or even those Gibbs methods might even already struggle in that setting, and then you might want to look into the Gaussian approximation. And if you observe frequently enough, often those approximate Gaussian methods actually work better. But it really depends on how much samples in the end you can generate.
Yeah, I was asking if you've tried in those intermediate situations, have people tried using these Gaussian approximations because they're so much faster than using PMMH or particle Gibbs. So if these approximate methods were pretty good, then even though they're approximate, we would use them instead of, say, variational Bayes or something like that.
Yeah, I think people should. There's a strong, also in the data estimation community, there's a lot of people who do kind of variational Bayes, but they also then have the Gaussian underlying approximation. I still think you should opt out for these particle methods then, because you actually can model the spread much better. In terms of, I don't know, it depends also on the communities if they know these methods well, and if they know these methods, I think people use them. And yeah, for also smaller dimensional problems. I think sometimes, for example, in the pharmacology example here, people actually didn't know about these methods. So we started to use them, and people were really excited that for these lower dimensional, because these are not 10 to the power of 8, they're much smaller, and people got really excited about the methods because I haven't really seen them before, and they were using more like maximum a posteriori kind of estimates.
Thank you.
Thank you for the question.
One last question from the chat.
Yeah, the initialization of the model definitely is very sensitive to the initial parameter setting. Of course, this varies also with the model, but yeah, of course, very sensitive to it. I guess if you've been observing data long enough, you will somehow settle into a parameter setting, hopefully, where it doesn't matter that much anymore. But yeah, of course, initialization does matter. And yeah. So this is still something, so not everything is perfect yet. So plenty of stuff to research on. So if you got excited about it, there's a lot of open questions still, open problems to solve.
Cool. Well, thanks again for a great talk. Thanks everyone for coming in the room and then coming online. I don't know if Sandy, you want to say a final word?
No, just wanted to say great talk, and yeah, thank you also to Boris for wrangling with all the IT issues and getting everything to work in the end.
That was not me.
Okay.
Yeah, thank you so much, Sahani. Can't wait to see you back
Yes.
somewhere in the world.
Yes, absolutely.
Bye everyone.